Morning, ladies and gentlemen, and welcome to the 59th Annual Congress of the Grassland Society of Southern Africa. Welcome, of course, to our in-house delegates here at Gariep in the Free State in South Africa, and welcome also to our online delegates who are joining us from elsewhere in the country and further abroad. So welcome all. We're now going to move on to our first session, and this is a special session on climate change and carbon. Now, carbon and climate change is of interest to many. I mean, it's not putting it down to say that it's of interest to a significant group, a significant proportion of the entire world's population. It's of importance in agriculture, it's important in conservation, it's important in industry, it's important in everything. It's important in politics, it's important in the whole world. And before this Congress, while we were discussing the structure of the program, the organizing committee ID'd this as an important area that we felt the society should really be focusing on. And so we wanted this as a bit of a central feature, certainly at this Congress and hopefully Congresses into the future. And it delights me that to speak about carbon, we have he's a distinguished researcher at Stellenbosch University. He's the acting director of School for Climate Studies, and his interests are wide and varied, but they certainly include a understanding of carbon from small to large levels, from Rubisco. You know what Rubisco is? You must check what Rubisco is if you don't. From Rubisco right up to global carbon fluxes and how that influences the world. So thank you very much for agreeing to come and give us our opening keynote presentation from Stellenbosch, Professor Guy Midgley.
Thank you, Justin, for the kind introduction. Thanks very much for the invitation to speak to you all. It's an honor to be able to share these ideas. And yeah, thanks for all the very fine arrangements. I think this is a fantastic conference. It's varied, it's packed full of content. And can I just say congratulations to the society for staying so vibrant, growing. These institutions are very important for the success of the country. And long may you live and grow and continue to increase in importance. You will have noticed that my title has changed a little bit. And the reason I've done that is to expand the vision of this talk and to talk a little bit more broadly about agriculture and its legacy through land use change and how that relates to carbon cycling. And I'm probably going to go back a little deeper into the past than you may suspect. But please join me for the journey. I think it's an interesting one, and I hope it's going to give you some deeper context. Justin opened by saying that a lot of the world is interested in carbon. And that is true. Because of recent events, extreme climate events, particularly in the developed world, which has largely been trying to do as much as they can to slow down action on climate change, suddenly, because of the impact of extreme events in North America and Europe and other parts of the developed world, there is a rush to attempt to draw carbon out of the atmosphere. There's also kind of a rush to reduce fossil fuel emissions, but if the burden can be shifted to drawing carbon out of the atmosphere, you know, that gets a lot of money. And there are big implications for Africa. There are big implications for our ecosystems. There are huge implications for agriculture. And they're not all good. And this Grassland Society needs to be very aware of what's going on. So I open with a picture of Alan Savory, who has on the internets, on the interwebs, a talk on the TED platform, which is about how to manage land. And it's a very interesting talk. It's probably the fourth or the fifth most downloaded TED talk. And I'm going to, spoiler alert, it's wrong. It's very wrong. I'm sure he's right on a number of things, but on this, he's very, very wrong. But it gives you an indication of how attractive this topic is. And he closes the talk, and I've paraphrased from his talk. Google it, you'll find it. It's very easy to find. And his message is, if we can restore about 50% of degraded grasslands using his methods, we will store enough carbon for thousands of years to return CO2 to pre-industrial levels. That is a very attractive message. And in fact, at the end of the talk, the guy who runs TED walks onto stage and says, you know, Alan, I want to hug you because you're going to save the world. And that is the silver bullet idea, which it just doesn't exist. I'm not saying agriculture is not important. It's incredibly important, but there's no silver bullet. All right. Just to warn you. Okay, let's have a look at this little picture. And I'm going to use this gorgeous this thing here. How does carbon cycle in our planet today? What you see here is the main person. This is not where, oh, I've got to do it here. Okay, so, all right, I've got you. Wow, this is more difficult than I thought. This is tons of carbon. This is, this is billions of tons of carbon, gigatons of carbon. There are 850 billion tons of carbon in our atmosphere today, which translates to about 420 parts per million. So from that, you can calculate, you know, every 2 gigatons that we emit into the atmosphere can turn into 1 part per million of CO2. But what's interesting is to look at where the carbon is and how it moves on an annual basis. And what you'll see is that there are 560 billion tons sitting in vegetation, in plants. But these plants are enormously active. They drag about 120 billion tons out of the atmosphere every year in photosynthesis. And they emit nearly another 120 back into the atmosphere. But it's not quite 120. You'll see that 59 and 58 is 3 short of 120. So in other words, what that means is that the terrestrial vegetation is absorbing 3 billion tons of carbon every year. Now that's a very big number. There's nothing in carbon dioxide removal that comes close to matching that number. Similarly, in the oceans take up 92 billion tons and they emit 90 billion. So they're taking up another 2 billion tons. They're sucking in 2 billion tons. And the result is that although we emit 10 billion tons from land use and from fossil fuels, only about 4 billion tons stays in the atmosphere. So that means that the natural environment is absorbing this carbon and saving us from a much higher rate of warming. This, I don't know what happened now. Oh, there we go. But look at this number. If we look at soils, it's like shaving in the mirror. You can see I cut myself this morning. It was really cold, that's why. 1,500 billion tons sitting in soil. You know, it's 3 times the amount that sits in plants. This is an enormous number. You know, it's twice the amount that sits in the atmosphere. So if we can find ways of getting this carbon sitting into soils or down into the rivers and into the oceans, it's already helping save the climate. Okay, so that's the background to the importance of land use and land management. Things of, you look how much is in the deep ocean, that needs to stay there. 32,000 billion tons in the deep ocean. Those are the sorts of numbers that can bubble up if we go crazy with climate, okay? Those are the risks. Now, let's look at what the projections are for the next 70 years or so. we face choices in the world. We can continue on the road that we're on, which is what we're doing, or we can turn things around and try and save ourselves. And this seems to be the most likely route that we're going to follow. We're going to follow some kind of an overshoot, and then after a few decades, we're going to bring things back. We hope. So we will go through an overshoot of some kind. And my question is, how on earth did we get to this position? How did we find ourselves here? And what do we do about it? And what role can agriculture play? Well, let's start by telling the story of our species, Homo sapiens. How long have we been on the planet? Our species has been on the planet about 250,000 years, about 250,000. Depends who you believe, but probably about 250,000 years. So we existed on a planet that, interestingly enough, was much colder, drier, and less productive than the world that we live in today. And that is because we live in an ice age. We live in an era called the Pleistocene. We're now in a thing called the Holocene and maybe something called the Anthropocene, but essentially it's a bit of a false description. We live in the Pleistocene. We are born in the ice age. We were born in the Pleistocene. And I guess it raises a question. If we were around on the planet for 250,000 years, why did it take so long for us to become the dominant species? We've only started to dominate the planet in the last 2,000 years. What on earth held us back for so many tens of thousands of years? We were essentially the same species, the same intelligence, the same abilities, but we were held back by something. So something must have changed to allow us to become dominant. Now, the social biologists and anthropologists will tell you, well, it's about human interactions and it's something about, language, invented language, and something happened and then suddenly something switched on and we became productive. I'm not sure that that's right. I think that it's a resource issue, and it's relevant to agriculture, as we'll see. So we know all this from ice core data. This is exceptionally well established. So what you see is right at the end of the Pleistocene. I can actually point it there. Oh, brilliant. Much easier. We see that about 20,000 years ago, the world was a really cold, dry, nasty place. Humans were hanging on by the skin of their teeth. And then things warm naturally because of the way the planetary system works. And then we get into this era of a fairly stable climate and a higher CO2 level. This is a crucial change. It changes the game for humans. Why is that? Well, one of the results is that the world becomes much more productive once the CO2 rises 18,000 years ago. If we look at the arrangement of biomes on the planet 18,000 years ago, it's very different from the arrangement of biomes today. You can see that forests, tropical forests, were beaten back into small enclaves. Trees nearly went extinct. And when things warm up, we see the forests expand, we see the savannas expand, we see the deserts contract as CO2 rises, rainfall rises, the planet becomes more productive. That is the context for what releases humans, because all of a sudden, as the planet becomes productive, plants become more productive, and it starts to make sense to farm. And farming is a lot safer than hunting big, nasty animals. And there was a big incentive to switch. And we can see that if you look at the evolution of farming, agriculture, you can trace it in the area of the Natufian region in the Middle East. We see that as the CO2 rises about 10,000 years ago, we suddenly start to see people using these kinds of tools, which are used to harvest grain crops. And that never happens before. It starts to happen, but only when the world warms and CO2 rises and crops become more productive. This is the trigger. It's not a social biological thing. It's a resource issue. And I'll just show you one graph to illustrate this. This is the response of wheat, modern day wheat, to CO2 level. So if we go back to these glacial levels, the production capacity of wheat is 60% lower than it is at pre-industrial CO2. So that's why it made no sense to farm, because crops just were not productive. And it's only once you get to these higher CO2 levels that suddenly these grain crops become productive, and that switches on an agricultural economy. What does that do? You start to generate excess. You start to generate the concept of money. You start to generate the concept of society, structure, city-states, and it sets all that stuff in trend. All right, I think that's an interesting idea. Now, what happened next? Well, the world went through a period called the Holocene thermal optimum. CO2 was nice and high. Things were productive. The Sahara was green at this point. The climate was different again. We had a green Sahara. The Sahel moved way further north, and something to do with the Indian Ocean, and I'm not going to go into it. But that's called the Holocene thermal optimum. And then the world starts to cool. And we were on our way back down into another glacial, into another ice age. But we started to do things that turned that trend around. In other words, we started to engineer our climate without knowing it. And agriculture was likely a key part of that. So you can see here, things were cooling down, and then we start to do some agriculture. And then we invent fossil fuels, and now we start to warm the world again, back into a sweet spot, we think. The trick is we don't want to go too high, we don't want to go too low. This is a Goldilocks argument. How do we achieve that? We could do things like this by 2021. We could go higher, and that could be destructive. So what happened a few thousand years ago? Well, there's some evidence that the invention of rice farming, and now you start to see agriculture take a center stage. Rice farming was invented in the Middle East, in the Far East, and you see the emissions of methane start to rise in the ice core record. And there are some who argue that this is one of the things that drove, and that starts to warm the world again and starts to counteract this natural tendency towards an ice age. And that's where rice was invented, and that's how it expanded over the years. Another really important form of agriculture was also invented around this time, and it happened in the Sahara, and that was the domestication of cattle. And if we look at the history of the domestication of cattle, it's very, very interesting, because cattle farming was invented here between 5,000 and 3,000 years ago. From the archaeological record, we see that the Sahara area was really the origin of the cattle cultures of the world, of Africa. And when the Sahara dries, 3,000 years ago, the Sahara dried. It must have been an incredibly scary climate change that happened, because the Sahara dried, and these cultures were forced to move south as the desert formed. And so they moved south into southern Africa, and the sheep and goat culture appeared to move somewhat towards the west and the south, and the cattle cultures moved towards the east and the south. And then they finally arrive in these areas somewhere around 1,000 years ago. And that spread of cattle and the rise in the use of cattle was also contributed to methane. Gotcha. And was part of this geoengineering of our climate. So the way that we now farm the world is a very, very important part of how we manage our climate. What do we face? What is the risk that we are facing now? Well, the risk is that today we are in a period of the highest rate of CO2 increase in 60 million years. There hasn't been a time in the last 60 million years where the rate of CO2 increase has been this high. That is a terrifying number. So CO2 is ahead of temperature It's gone ahead of climate. So in other words, we're committed to a certain climate change unless we do something about the CO2. And these are the scenarios that we face. Now, what if ecosystems, how have they helped us? And how can land management and agricultural development help us manage this further? Well, just one way to point this out is to show you that the CO2 level in the atmosphere in 1870 was just under 300 parts per million. And today it is 390, well, no, when this paper was done, 2014, 400. We're now at 420, over 420. And what we see is that if all the fossil fuel emissions and land use emissions had stayed in the atmosphere, we would be 150 parts per million higher. But about 75 ppm have gone into the land and about 73 into the ocean. So we would have been at 450 ppm. Temperature would have been a couple of degrees hotter, and we would have climate chaos today. So our natural ecosystems have saved us from disaster. And it's happening here in this photosynthesis thing and in the photosynthesis process. But we don't know where it's going on land. We know that 2 to 3 gigatons are going into the land. We don't know where very well. All right. Now, we're starting to get a handle on it, and it's very relevant to how we manage land. We now know that because the CO2 in the atmosphere is so out of balance with natural processes, it's obviously out of balance because so much is moving into the land and moving into the oceans. What is the effect on land? The effect is called CO2 fertilization. And recent work, this is a 2021 paper, I think, it's a 2022, 2023 paper, and it shows that CO2 fertilization has increased photosynthesis by about 13 to 16 billion tons of carbon per year. Obviously, respiration has also gone up. So, but where is this happening? The theory suggests that the sinks are, many of these sinks that are switched on and are in semi-arid regions of the world. And if you look at these colors, these are where the big sinks are, these are where the small sinks are. And you can see that these subtropical systems, like here, are part of the sink areas of the world. There appears to be a big sink. It's just, these are relative numbers. So a small change in a small number gives you a high number. So that's why the Sahara comes out. So, but these are decent changes in decent numbers here in the subtropics. And this is a part of the world like around here where the world is warming, CO2 is going up, rainfall, we don't quite know, seasonality might be shifting, but these systems become more productive. These are systems that have become a lot more productive in the last 10 to 20, 30 years. And you're seeing the more net primary production on these systems here. How do we manage them? And can we use it to capture carbon? Well, that means I've got 10 minutes left, 9 minutes left, of 45 or of 30. Okay, that's fine. I'm actually nearly done. So now, that means that farmers in these regions are sitting on a system that's increasing in net primary production, if managed correctly, and are sitting on a system where carbon could be stored in the soil and could be monetized, given different management regimes, because the world is crying for carbon storage. There's big money going into carbon storage, carbon sequestration it's called. Or if you want to really get serious, carbon dioxide removal, CDR, which means storing it and putting it away for thousands of years, as Savory sort of suggested incorrectly could happen. Now, one of the ways, we don't have a lot of information in Southern Africa on how this actually works. And one of the ways you measure this is with these instruments called flux towers that can measure the CO2 and water vapor exchange. We've got about 5 or 6, maybe 10 in Africa. there are about 1,000 of these things scattered throughout Europe, maybe more, several thousand scattered throughout Europe and North America, and nations which are rich are measuring these fluxes at a very high resolution. But we don't have that capacity here. So it's a vulnerability for us. So we can get messages from the Northern Hemisphere saying, hey, you guys need to manage your land like this or like this. You need to plant trees because you're going to store carbon. We don't have a way. Yeah, we don't have a really quick way of testing that because we just don't have the resources. And one of the big inequities in the world is that Africa's share of the climate change science budget is less than 3%. The continent most vulnerable to climate change and least responsible gets less than 3% of the global investment in climate change science. And half of that goes to developed country scientists working in Africa. So African scientists and African capacity gets less than 1.5% of the global investment. That's a shocking figure. And it's one of the reasons why we have so little capability. The result is that African countries invest about 3 times the GDP portion in science investment into climate change science. 3 to 4 times. Just for noting. Anyway, so one of the pieces of equipment that we could really use to do this is these flux towers. And fortunately, we have some flux towers in the Karoo, and I'm going to show you some data at a site that Justin has helped to manage for many years. But you can see here, this is what a flux tower looks like in the Karoo, because the Karoo's short vegetation, they don't have to be very tall. Here's another flux tower at Benfontein near Kimberley, because it's got tall trees, the tower's got to be a real tower. And we've been measuring in these 2 sites for some years. Now, what do you measure? Well, you measure the water vapor use. During the day, vegetation gives off water vapor and it takes up CO2. So there's some nifty equipment here that's just measuring continuously the flux of CO2 up, water vapor. It's measuring it all the time, actually at microsecond scale. And then there's some software in the here that translates that into fluxes. And these are pretty precise measurements. You can measure the respiration from the soil. You need a lot of money to measure methane. We don't have that kind of money, but it would be very useful for us to measure methane because we could measure things like termite activity and other things. And then another thing that we have to calculate or fill in the missing pieces of the puzzle because we don't measure it directly is how much carbon goes down into roots and and goes out into the soil and then floods out into the ocean. And because plants exude a lot of carbon through their roots into the soil to control the soil conditions, to grow the kind of bacteria that they need and to change the pH. Plants don't passively sit in soil. They actively manage their own soil. It's very important. And that interacts with how plants are managed. If you overgraze a plant, you take away resources for it to manage its own soil. And it could be one of the routes by which you change the competitiveness of a sward or of a natural rangeland. Now, I'm just about at the end here. I'm just going to give you a little insight into some data that we measured over 4 or 5 years at Middelburg on 2 Karoo sites that had different land use histories. One site was heavily overgrazed for about 30 or 40 years. Justin will correct me. And then stock was removed. And the other site has been grazed at the recommended stocking rate for decades. And what you see here is the data for the 2 sites. And this number, the net ecosystem exchange, is how much carbon is that system absorbing. If it's a positive number, it means that it's losing carbon to the atmosphere. If it's a negative number, it means that it's sucking carbon out of it, it's storing carbon. Now that's, if you're into the carbon game, that's what you want. And we see that over the years, there's a very strong seasonal pattern. In the rainy season, you see the storage going on, and then as it dries out, you see release, and then the next rainy season, you get storage. So rainfall, temperature, seasonality play a role, but it is the degraded system that is recovering from degradation that is the red line, and it's scoring carbon over time. And as soon as stock was reintroduced to the system, it started to lose that capacity. This is the naturally managed system, and it seems to be a little bit negative, but it could be roughly neutral. This is the difference between those two systems. And it shows you the enormous legacy of past land use, because the difference suggests that the overgraze system that's recovering is now in a sink state. It's absorbing carbon. Now, we need a lot more of this kind of work to figure out what is the best way to manage these systems. And it's not only about how the vegetation is responding, and it's also about how the animals and the different breeds of animal and the different species of stock animal interact with that vegetation. What is their, what sort of digestion do they have? We need to understand far better. Do you want to use merino? Do you want to use dorper? All those different species are going to have, and breeds are going to have different ways in which they interact with shrubs, with grasses of different species. And that's the kind of precision rangeland management that we would really, I think, need to get to be able to credibly sell and verify that we know what we're doing with respect to grazing. So, Justin and I have visited some really interesting plots near Middelburg, where the farmer knows a lot about digestion. He can interpret the dung of his animals to show whether they are productive or not, and he knows by how much lick is being bought, how much of the vegetation they're using, and how much they need support. This is the kind of precision management that we need to get to. All right. Why do we need to know this? Well, we need to know this because the grasslands and the rangelands are under a really distinct threat. And the threat is that the world wants to find large areas of land to plant trees, because their vision is that the forest is the ultimate ecosystem. Everybody wants forests, of course, because forests are just great. Now, we don't really think that. Grasslands are great, and shrublands are great. We don't want forests everywhere. In fact, our highest diversity ecosystems are not forest ecosystems. But the world has been putting hundreds of millions of euros and dollars into identifying areas where they can encourage locals to plant trees to store carbon. It doesn't work. Number one, the carbon storage doesn't really work because you're replacing what the grassland is storing. And number two, because you change the nature of the vegetation, you actually can even cause local warming, because trees are darker than grasses. Grasses reflect. So this is the risk to Africa of afforestation. And believe me, all this investment in the Great Green Wall and planting eucalyptus is a threat to grasslands, a threat to the very name in your society. And you can see the risk on the left, the systems under risk are these grassy biomes at risk of afforestation. This is from the IPCC report and from a paper that we wrote. These are the risks to our grazing animals, our carnivores, and to cattle production. These investments will change the culture of local people for decades, for generations to come, if they're successful, because they will remove these grazing lands and these browsing lands. So just to close, my colleague Pedro Montero and I have written a paper in SA Journal of Science saying what we really need is we need to build a national and a regional partnership to understand the policy around these interventions. And we want to engage with institutions like this to understand how you see the risks and how we can get information from this. We think it's vital. It's going to have to happen over the next 10 to 15 years if it's going to make a difference. We don't have a lot of time. We have some time, but it is critical that we achieve this. And yeah, we'd like to stay very much engaged with the community and understand the problems that you have and the opportunities that exist. So thanks very much for listening.
Guy, thank you very, very much. I had high expectations and my expectations have been exceeded. Thank you very, very much. What we're going to do is we have about 15 minutes to discuss this. During the session, we're then going to have other talks, and at the end, we have another few minutes for discussion. So I'd like to now open up to the audience to ask questions. I think that we have a couple of microphones around. Is that correct? Is that the way it works? Okay. So what you do is if you want to ask a question, stick your hand up and then we'll have a microphone delivered to you so that all of these questions and responses can be recorded. So opening to the floor. Lorraine.
Thank you very much, Guy. I think everybody involved in agriculture found that really, really interesting. The question that I have, and it's a question that came from some of our livestock farmers a couple of years back. They were really interested in at that time, how do I get money for this? But the actual question was, as a livestock farmer in the Karoo, what type of diversification can you have on your farm to increase that whole carbon sink or capturing carbon? They heard about the whole speckworm planting and so on, and they have frost. So what type of diversification can a livestock farm in the Karoo do?
Yeah, great practical question. Well, I'm not so sure you need diversification, but I think what's clear is that different management regimes have different effects in different places. So you can't, there's no silver bullet. But what we need to understand is how the underlying soil type, sands versus clays, nutrient content of the soils, the vegetation types, the balance of shrubs versus grasses, the species of shrubs. These are all critical things which would inform your management decisions, and it gives you the basic information you need to know how to manage to store carbon. And that knowledge is fragmentary. There are a few experiments that we can draw on, but I think there's a fair amount of work that we need to do to fill in the gaps, because these are can be patchy systems. So I think it's too early to be able to answer that question with any confidence. But what's really going to be valuable is to gather as much information from as many farmers as possible who are measuring carbon on their land and the change in carbon, and start to put that together in a model. But we need to do that PDQ because the time is rushing and the pressure's on. So we have to coordinate, and there is big money available in it if we get it right. I can hear, but it doesn't need to be on. Yeah, Zoom people must hear. Yeah.
There we go. Great talk. Thanks, Guy. Lots of questions, many questions, but got to restrict them. First of all, you compared to systems one which wasn't grazed with one that was grazed. I'm not sure in which manner. And, that there is a lot of push in addition to forestation as to destocking and tiling, getting rid of cattle and going to whatever, some plant-based meat, whatever the heck that is. And I think it's a problematic message, because in fact, livestock in many instances can be used quite usefully to improve systems. And so one of the questions that comes out of that is, what is the benefit of having livestock on rangelands for increasing arthropods, which is a critical aspect that people talk about microbes, but arthropods are often not talked about. And that's a really critical aspect. So that's the one question. And the second question, real quick, is the idea of paying people to improve degraded land versus paying people to maintain land that's been well managed is also really problematic, because it actually creates a massive disincentive structure for people to degrade land and then to improve it again.
Yeah, first one's a science question, second one's a policy question. course, we have to graze these systems. We have to browse these systems. That's how they evolved. Yeah, the indigenous animals that were probably in their millions across this landscape. You know, can you imagine how many millions of animals were roaming this landscape before people emerged? We've replaced them with different kinds of animals. And that, for me, is the critical thing. Can we understand the digestion, the grazing pattern, the behavior of the animals that we now manage versus the original animals? And it may not be exactly the same, but if we just understand it, we can then entrain and use the natural processes to get that carbon storage going. I'm pretty sure it's possible. I mean, it has to be, because it's happening. CO2 fertilization is working, but we need to be more deliberate about it. The second question was the policy question about incentives. And it comes down to a word called additionality, as you probably well know. What does additionality mean? It means you get paid for doing something that would not have happened otherwise. So if you are managing well already and you're storing carbon, you're not going to get incentivized by these schemes because there's no additionality. You're not doing anything different. The degraded lands are the ones that get additionality. And so you saw in the negotiation around deforestation, restoring forests, yeah, what baseline do you use? Because that tells you, and there were possibly even incentives to deforest in advance of that baseline being set, so that then you had land to afforest and make money out of. This is a very difficult game, and it's a political game, it's an economic game. So you have to go in with your eyes wide open. And it's understanding the science, understanding the politics is not so easy. That's why we're arguing we need the CDR partnership to guide. It's a science policy hub to guide people from the science through to the politics and the economics. You've got to get that joined up. Otherwise, you can get it very wrong. And we've seen disasters happen. So great questions. Thank you.
Thank you. Thanks for a nice presentation. Just have two questions when it comes to the increase of carbon. The one question is, what is the relationship between the carbon increase and the, either you call it bush encroachment or invasive plant in our grazing land? And the second one could be close to it, like to say, in terms of increasing the carbon sink, because it comes clear to me that we can eradicate trees. We might somehow, I don't know, perpetuate the problem. But then between the invasive trees and the indigenous trees or plants, is it possible that they might have a different effect in terms of carbon sequestration?
No, that's a really good question. Yeah, it's a little bit contentious, but my view is that a large chunk of the natural bush encroachment we're seeing is driven by CO2 fertilization. I don't think it's possible to deny it. It has to be that way because plants become more efficient with water. It's like adding rain, basically. So, and woody plants that need more carbon to build their bodies. You know, grasses don't need a lot of carbon. They just make leaves and roots. Trees have to use a lot of carbon to make the stems. And so it makes sense that the woody plants, and in fact, if you go back in deep time when CO2 was 2,000 parts per million, way higher, the world was covered by forests. It was covered by forests. These savanna and grassland systems only evolved once CO2 dropped below about 500 parts per million. And it's only about 15 million years ago to about 5 million years ago. So, and some people are considering pushing CO2 up to 700 parts per million. Under those conditions, grasslands did not exist. We could see the complete eradication of grasslands through wood encroachment. Now, do encroached systems store more carbon than grasslands? That's a brilliant question. We don't know the answer. And in Namibia, where they claim woody encroachment as a carbon sink, there is now a massive industry in bush cutting endemic invasives and turning it into charcoal. It's a lucrative industry, and it saves biodiversity because you save all the grassland birds and the cheetah and all this and stuff. So my view is that with this level of CO2 and high levels of CO2, we've started to evolve an inexhaustible supply of endemic wood across our landscapes. And we're going to have to figure out what to do with it. If we just let it take over, we're going to lose massive amounts of biodiversity. We're going to lose hydrological services. We're going to lose grazing lands. We're going to change our culture irrevocably. We are facing the problem of what are we going to do about this invasive wood? And it's not only invasive species, it's endemics. And the first responders are the nitrogen fixers. There's a set of species that's been the first to respond. But that doesn't mean that other species are going to respond later, because you need more nitrogen in the soil to really respond. And those nitrogen fixers are the ones that are taking off. And in fact, there's a group at Rhodes under Brad Ripley, which is starting to uncover the secrets of what is behind the first responders. But I don't think it's going to go much further than that if we let it go. Great question. And we don't know the answer. Sorry to say. Yet.
Thanks, Guy, for a great talk. I think Urs has already kind of asked my question, but I just want to follow up on it. As I find it hugely problematic and cynical to financially reward that additionality, whether it's forest or whether it's grasslands, when, you know, someone who has managed their grassland for 200 years really well has prevented all this CO2 from going into the atmosphere. But then what I wanted to follow up on is, I mean, with RED Plus, for example, I mean, there is also reward for avoided deforestation. And is there not the potential for such a mechanism for other ecosystems as well? Because if you don't plow your grasslands and turn them into something that loses all that locked up soil carbon, there should be an incentive for that.
That's a brilliant point. RED Plus, for those who don't know, is reducing emissions from deforestation. It was put in place, was originally intended to be part of the Kyoto Protocol back in the 90s, but it was never implemented because people didn't trust the countries that were deforesting, and there was not enough satellite imagery to be able to track. So what RED did was said, okay, we're now going to incentivize people to not deforest, so you can get monetary gain by keeping your forests for the first time. But there are problems, of course. So you don't deforest in one area, but then it leaks out and you get deforestation. So in another area. So it's very difficult to manage. You need to monitor it from space very, very carefully. But that's a great point. And you know, but the additionality there is you've got to be able to prove that you were about to deforest in the next 10 years. Why do you think, why are you so surprised by the cynicism of the financial system? I mean, our whole financial system is basically sociopathic. I mean, if you look at why do interest rates increase? It's to push people into poverty so they don't spend as much. Interest rates increase in the US to increase unemployment. That's what they're trying to achieve. It is essentially a sociopathic system. So don't ever be surprised that it's cynical. It is deeply, deeply cynical. If we could change that, it'd be phenomenal. But never be surprised about cynicism in the financial system. It's embedded. It's entrenched.
Richard at the back.
Hi, Guy, thanks for that talk. Yeah, I think when it comes to thinking about how to manage these grasslands for carbon storage, one of the issues I think is trying to understand how the spatial and temporal, how animals are managed spatially and temporally. You know, and I think this is, I'll present some data for this tomorrow. That
excellent.
Under rotational grazing systems, which we thought were great, actually there's a lot of problems with that, because I think they result in greatly reduced root production in your soils. For so when a grass produces a lot of roots, then that's got to be storing carbon. You know, it's pumping carbon into the soil. But under rotational grazing systems that we're using, where we're grazing and resting in the same season. We're taking a paddock and we're resting it and we're grazing it in the same season. That has a lot of problems. And I'll show you the data for that tomorrow, which if you switch to seasonal year-long resting of half the farm and year-long grazing of the other half, that changes the dynamics a lot. So I think these are the sort of things that we can look at. We need to start looking at shifting our whole mindset about how to manage animals. Yeah. So
it's a great comment. I mean, it's not a question, but the important thing is abandon ideology. Don't be ideological. Don't be religious about your belief about how land should be managed, because you could be wrong. Richard Feynman, the great physicist, always said, the easiest person to fool is yourself. Abandon ideology, look at the data, and be humble enough to say, actually, that was wrong. I blew it. This is the better thing. And we need experiments. We need people like you doing this work. There's also an issue about size and size of land and how you move stock around. There's a lot of things to think about here. But yeah, great comments. Thanks.
I'm asking or commenting on behalf of Sigrun, who's online. She says, in terms of carbon storage for pastures, it seems that companies just want one broad parameter to measure and are not really interested in too many individual parameters to define the value of a system. It's more a comment than a question.
It's true. And that is also, it's a cynical view, because you're looking at carbon, say carbon stored in the soil. But how do we know how much carbon is actually being exuded by roots, flowing out into the water, soil water, and flowing into the ocean, which is a long-term storage? It could be twice as much, and you're just missing it. We don't measure it. So there's an element of better science that's needed as well for us to really understand what's going on. And all the models that are used to reconstruct what's happening to the global carbon balance doesn't have a root exudation component in it. Maybe 20% of the whole carbon balance. That's 20% of that 90 billion tons. That's 25 billion tons. So and the Northern Hemisphere isn't focusing on it. And because we don't get the money to do the research, we're hamstrung. So we've got to fight for that. Our negotiators have to fight for Africa better. It's unacceptable that we get so little, and communities like this are deprived. Yeah, the world doesn't care about Africa, guys. Let me just.
Thanks, Guy. That was a great talk. And maybe continuing slightly on the cynical line, can you comment on the regenerative agriculture movement? There's a big move to push regenerative agriculture, which sounds fantastic in principle. But many of the ways that regenerative agriculture is assessed is a process-based assessment rather than outcomes-based assessment. So in other words, if you do A, B, and C, you tick the boxes and you get paid. And there are people getting paid for carbon storage and things and various things just by ticking a few boxes. Are they actually storing carbon? Do we know enough to actually promote that kind of approach, or what?
Good point. Fluxes and stocks, flows and stocks. You have to measure both. You can't measure one or the other and think you got the answer. If you can define regenerative, I would really be excited to get a strong definition of what regenerative agriculture includes, because it sounds like a useful idea, but I don't know enough about what is the definition of regenerative agriculture. I'm a bit behind the curve on that, but it's about stocks and flows, processes and stores. You have to measure both. Good.
You mentioned South Africa doesn't have many methane measuring instruments in South Africa.
Just about none.
Do you perhaps know how reliable satellite emission monitoring satellite sites would be, or monitoring in South Africa, for example?
That's a great question. I'm not an expert, but I think those measures are getting better and better. I know the CO2 measurements are getting much better. I'm not sure how precise they are, so whether you can identify points. I know that the CO2 systems can identify points, big point sources. But a lot of these emissions are small, but over vast areas. And I think that's a bit of a challenge for the satellites. But it's a very, very good question. I can't answer you with confidence. So Google it and come and tell me. I'm also going to Google it.
Just also to add on to that quickly, like since we don't have our own instruments, we also can't validate it exactly in South Africa.
That is true. That is true. And we have found that with some of these NPP, net primary productivity measures, models, they don't tie up with what we actually measure on the ground. And it's because they've got assumptions that are based on other kinds of vegetation that are imported into our vegetation, which is different. And so we are it's underestimated how much our NPP is and how much our carbon sequestration is. And that's wrong. It leaves us in a bad position. So, got to sharpen up. Great question. Okay.
Guy, thank you so much. We don't have time for more questions at the moment, but there will be a short time for discussion, actually not that short, after this, once we've listened to other presentations, and then we can, anyone who still wanted to field a question will have the opportunity to do so slightly later. And our next speaker, could I ask up Sibusiso Dlamini, who's going to be talking about soil flux measurements at the Brotherton Plateau.
Right. Good morning. My name is Sibusiso Dlamini, and I'm a microbial community ecologist. And what I'm presenting here is a section of my work looking at the abundance, the diversity, and the activity of microbial communities as influenced by fire and experimental warming in Brotherton, Drakensberg. As the prof has said, many of these systems function based on how they're either managed and how they're interconnected. And in my case, I'm trying to understand how fire and experimental warming influences decomposition and microbial activities, which then, of course, results to different rates of respiration in this ecosystem. And of course, grasslands cover like a significant part of the earth, and therefore that's why they're very important. And respiration accounts for the highest terrestrial carbon flux or movement. And studies have shown that more frequent fires can increase the rates of respiration, and increase in soil temperatures or changes in soil moisture also can influence soil respiration. And this is seen to be different in different seasons. So with the increase in temperatures due to climate change, it is therefore important for us to understand how fire frequencies, experimental warming, and hydrothermal factors would then influence soil respiration. And therefore, that's why we are quantifying the rates of the respiration as influenced by these three factors. And we aim to quantify the rate of soil respiration as influenced by the factors I've mentioned. And the question that we had in mind, does an interaction of warming and different fire frequencies influence soil respiration? And what is the influence of both soil temperature and moisture on soil respiration in my experimental site? And so the study characteristics is presented in the table on my right, and on a satellite image in winter on my experimental site looks like that. And sampling normally started in the morning at 9 a.m. somewhere here and going up the other way around. And the experimental design is, so we have 4 fire frequencies that are all replicated 4 times. And there's, in the periphery of those fire frequencies, open top chambers were installed to mimic warming, experimental warming. And my study focuses on the spring burns. And for data collection, we collected data in the summer and the winter season. And respiration measurements were done in the morning from 9 a.m. till around 11:30 a.m. for 14 consecutive days, both in summer and winter. And the equipment we were using is the Leica 8100 portable flux machine, which is clamped on a PVC collar, and 3 readings were taken for each collar in each fire frequency and warming treatment. And next to the IGA, the infrared gas analyzer here, is a temperature and moisture logger, which recorded soil temperature and moisture for 15 minutes intervals. And those readings or recordings were then linked to the time of the soil respiration measurement that we did. And our data failed a normality test, and therefore we moved into analyzing it using a Kruskal-Willis and Dunn test, and to have a temperature coefficient Q10 value, that equation was used. And for the repeated measurements, a linear mixed model was used to see how the predictor variables influence respiration, and further to understand the pathway analysis by the predictor variables, a structural equation model was also used. And obviously, best fit of these models was informed by the Akeki information criterion, because as you would understand, these models are a stepwise process where you first include one predictor variables and you keep on growing the model until you get a best one that looks like a best fit. And so in summer, a trend we saw was that, first of all, the warming chambers increased respiration. So in this case, the warming chambers are represented by the annotation OTC and the color red. And also the more frequently burned plots, the annual and the biannual, had higher respiration than the less frequently burned plots. And the Q10 values were calculated for the 5 frequencies alone and the warming treatments alone. And in the summer season, what we saw was that based on the Q10 values, respiration was more sensitive to the 5 frequencies than the warming, probably because in summer, almost all the resources that the ecosystem needs to breathe is there. And then the differences that we have is just based on the different 5 frequencies in the plots. And then in winter, we again saw the same trend that warming, of course, does increase soil respiration. However, as compared to summer in this case, biannual and no burn, interestingly, had relatively the highest respirations as compared to annual and quinquennial. And then in terms of the Q10 values, what we found in summer was that in this case, warming is respiration was more sensitive to warming in this case. And probably because with the ecosystem being a little bit more dominant, if you increase temperature, then by warming, you're sort of activating some of the microbes to be able to continue metabolizing. And we did the same test on the soil temperature and moisture for both seasons, and we found significant differences. And the trends in the temperature and moisture were following the same trends that we're seeing in the respirations for the different seasons as well. And for the linear mixed model, what we found was that, again, the interaction of fire frequency and the warming is a much better fit model, as shown by model 2 and the criterion indices here, which of course goes back to the fact that we have the warming chambers as an interaction of the fire frequencies as well. So as the warming chambers increase the soil temperature, our respiration, of course, then increases as well. And our structural equation model also indicated the same thing, that there's a strong and positive correlation between warming and soil temperature and its influence on soil respiration as compared to warming and volumetric water. And we found a negative response, or rather pathway from fire to soil temperature and so on, which then again emphasizes our point that in this ecosystem, the warming is more of a driving factor for soil respiration. And so the question to pose to the audience is, so do we burn and when? And before I get answers from you guys, let's consider a few points. From this study, of course, we found that warming treatment increases soil respiration, which was not a surprise. And that in summer, of course, respiration was more sensitive to the fire frequencies, and yet in winter, it was more sensitive to the warming treatments. And based on the models, of course, the interaction of fire frequencies and warming have a much stronger effect on soil respiration. And from literature that has been published in the experimental side, of course, another question is, do we want to be managing the ecosystem to be more of a source or a sink? And probably more frequent burning between annual and biannual is still somewhat considered to be a great and standard practice in the ecosystem. And grass species in the ecosystem are somewhat resilient to long-term fires. But of course, installation of warming chambers did influence them a bit. And spring annual burns sort of increase soil organic carbon and soil organic nitrogen. And while less frequently burned plots have relatively low carbon as compared to the more frequently burned, which then was evident in the respiration rates that we saw as well. But I would probably say maybe in future, we might consider burning less frequently to offset the increase of soil respiration by global warming, of which in this case was mimicked by the open top chambers in our study. And I would like to acknowledge the following organizations, and particularly the Grassland Society for funding my attendance for this conference, NRF Seon as Mvelo for awarding me a permit to go sample, and my microbial community ecology lab and JP Max Education Trust Fund for funding my studies. Thank you.
Thank you very much. We have a couple of minutes for some questions, if there are any. Can we have the microphone up here?
Hi, thanks for that cool study. I really like the structural equation modeling.
Yeah.
Because of the way it really shows which pathway has got the greatest effect. I was just wondering what the R squared was. How much of the variation in flux did that model explain?
I would have to double check the numbers for you, but can I just check that and then we'll have a chat on it? Yeah.
Hi there. Also on your SCM, on your coefficients for the fire and the soil warming, you had those as negative.
Yeah.
So was that, sounds like that's not what we might expect. And I'm just wondering how you had that coded, how you had do you have your fire frequencies coded, or you as fire frequency or as like time since fire?
It was just fire frequencies. So so I had them as annual, biannual, quinquennial, and no burn. So because the model can't pick up characters, so I had to change that into numbers. So annual being 1, 2, 5, and 0.
So you're saying the more frequently they were burned, the cooler the soil was.
Yeah.
Is that what you expected to see?
Not really, but that is what it came out. So.
And do you have information at least on what the time since fire was at that time?
Yeah, I can share that.
That's a really interesting study that you're doing. I've seen you looking at fire frequency, but is there a difference that you're seeing with fire intensities, like with low intensity fires and high intensity fires? Or is that outside the scope of your study?
Yes, that was, but my burns are the spring burns. So mostly in summer you have high biomass growth, and then you shift to spring it starts to die off. But of course, I think between the autumn and probably the spring, the intensity will be different, but that's not what I'm looking at. The reason I'm looking for, I'd rather in the spring burns is because the OTC chambers are only installed on the spring burns. So I wanted to compare the fire frequencies and the warming chambers.
Congratulations on a great study. I mean, soil respiration is one of the things we understand the least. So, yeah, I think it's very tricky to interpret these data. So don't feel like you're struggling for nothing. This is really, really important work. And I just want to say that we need more of these kinds of studies to fill in the pieces of the puzzle.
Yeah.
So I think this one looks really excellent. So congratulations. I just want to say that.
Yeah, thank you.
Look forward to seeing those results getting published.
Thanks. Maybe just to add on that, so the other chapters I have look at microbial abundance and diversity, so alpha and beta diversity. So, but a prelim analysis that I've done on the relative abundance using step bars, the different fire frequencies also have differences in the phylum groups. So you have a change from your acidiobacteria to, in terms of bacteria and or fungi. So there should be another explanation there that can explain further on the question you also asked as well.
Brilliant answer. That's a very useful study.
Thank you. We'll end it there. Our next speaker is Linda Kuchler-Dlamini, who's going to be talking about fire exclusion and soil respiration.
Good morning, everyone. Have to learn how to use this. So this is a small section of my PhD. My PhD was a joint PhD between the University of the Free State. I did spend some time here in Free State, but it's really cold here. So, and a university in France, in Burgundy. So some of the analyses, lab analyses were done in France. So this study looks at fire exclusion and aspect on its influence on seasonal variation in soil respiration and temperature sensitivity. So we know that Afro-montane grasslands are important. They are found in high altitude regions with high rainfall, summer rainfall, and they have high plant diversity and high endemism. And they provide various ecosystem services, which include water delivery and water storage, and they have high carbon stocks, huge potential for sequestration of carbon. But the problem is they are found in a climatic envelope that can support trees. So without fire, while they are ancient grasslands that co-evolve with fire, without fire, they change into a forest type system. And the impact of that change is not known, particularly on how it affects soil carbon and soil respiration. And also they are in mountainous systems. So they are south-facing slope and north-facing slope. And we don't know how that affects carbon and respiration. Soil organic carbon research have grown over the years. And I think it's because of few reasons. One, that soils are the largest reservoir of carbon. And there is concern about growing CO2 levels. And soils also release more some CO2 into the atmosphere. And this release, or the amount of CO2 released from the soil, is sensitive to temperature and land use changes. And the other hope is if we manage our soils or our systems well, or improve our soils through land management, we can sequester some of the CO2 in the atmosphere and store it into the soil. But that is bringing this problem that Prof was talking about of tree planting. So there's been proposals to plant more trees into these open system grassy systems. And you can see commitment on African countries that are willing to plant trees in these open systems. And these overlook these high carbon stocks and wildfires, because these are fire-driven systems, and the trees they are planting are susceptible to fires. So this brings me into my questions. I have 3 questions. I'm going to try to finish before time. The first one is on fire exclusion. So fire exclusion led into a forest type system. So it's a fire exclusion driven afforestation. It's not trees being planted, but it's because the system changed in how it's managed. So I'm looking at soil carbon stocks, isotopic signature, and then soil respiration and Q10. The second one is looking at aspect, south facing and north facing. And lastly, we're looking at the 2 measurement of soil respiration. There is one where you measure soil respiration yourself, and there is the LICO that the other Dlamini spoke about. So my study is in Kadrira Peak Research Catchment. It's just next to the Brotherton one. So we're moving to the catchment, not the burning treatment. So it was established in the 1940s to look at what is the impact of fire management and afforestation on water. So it was focusing on water, but we're utilizing these catchments to answer different questions now. So the 2 catchments I'm looking at is catchment 9 and catchment 6. Catchment 9 is south facing, catchment 6 is north facing. Catchment 9 was excluded with fire in the 1950s. So the exclusion of fire led into a change into a forest type system. So it's dominated by woody plants, Leucicidia and Badlia. But because it's a fire-driven system, you still have around the catchment a patch of grassland to compare what happens when you change the system. Catchment 6 is managed using fire by annual ban. So it's banned every 2nd year. So looking at the first question, so I looked at the carbon stocks and then respiration. So I'm comparing an afforested site to a periodically banned grassland, accidental fire. So we're not banning, it's just fires that come through. So looking at what happens when you change a grassland into a forest. So I collected soil samples down to 1 meter. And then when we look at soil carbon stocks, surprisingly, contrary to what people will think, the grasslands actually have more soil carbon stocks compared to the forest type system. But when you look at the whole profile, there are no differences, which means there is carbon in the subsoil under the forest. And then we looked at where does this carbon come from, looking at the carbon isotopic signature. So we saw that under, I don't know how to use the pointer, but the red one, under the grassland, you can see that carbon mostly comes from the C4 dominated system, so grasses. Under the forest type system, in the top, negative 26 and negative 22 around what you can see in a close savanna. So that's expected. But as you go down the depth, you see that it's moving towards a C4 dominated system. And when we do the isotopic mixing equation to look at where does the carbon come from, we see that in the subsoil, more than 40% of that carbon comes from the C4 grasses. So it's the old carbon, the legacy effect of when the system wasn't changed. And this is known in literature. The legacy effect is reported in volcanic soils like the ones in the Drakensberg. And then I looked at soil respiration. Unfortunately, I didn't have much money to have the portable LICO, so I had to collect the samples myself. So we create our own chambers, and you use a syringe to sample the gases at set time interval, and then you analyze the CO2 and do the calculation yourself. And you have a soil microstation that measures soil temperature, air temperature, barometric pressure, and soil moisture. So when we look at the data, we saw that between the two catchment, between the two sites, the afforested site and the natural grassland, you see that it also depends on when you last burnt or when last fire happened. So the first growing season after fire, there were no differences between the forest and the adjacent grassland. But as the grassland recovers in the second growing season, you see that the grassland releases less CO2 to the atmosphere and the forest remains in terms of how much it releases. So it ends up releasing more. So it depends on when last you burn and how frequent you burn, because fire triggers microbial activity and there is more soil temperature after fire because there are no grasses covering the soil. But we also looked at the linear mixed effect models, and we saw that this was controlled by a combination of soil temperature and soil moisture. So when we look at the temperature sensitivity, which is a Q10 value, the afforested site or the forest site have almost double the Q10. So it's more sensitive to changes in soil temperature than the grassland. And the grassland is around 2.5, which is normal. It's an expected value in temperate regions. We're moving to the second question. So the second question is looking at aspect. So for aspects, we're comparing a natural grassland to a natural grassland. So no need to look at isotopic signature, but we did look at the differences in stocks. We saw that the south-facing one, which is generally warmer, which is generally cooler and wetter, has more carbon stocks than the north-facing one. When we look at soil respiration, we also saw that it also depends on when last did you burn. So the first year, when I started sampling, the accidental fire happened in 2019. And in 2020, there was fire in the north-facing slope. So there were no differences in the first year after fire, but because the north-facing one is also warmer and there was fire after I sampled, so there was more respiration. And this is also controlled by a combination of soil moisture and soil temperature. And then we saw that the north-facing slope has more Q10 because it's warmer. And the last question is looking at the two ways of measuring soil respiration. So this LICO is the stationary one, measures soil respiration every hour. So it's fine scale compared to Lindo measuring soil respiration every month, going there for 3 years. But they were next to each other, allowing us to compare between these two. So when we compared the data, the LICO does require some care. So there was COVID-19, so there is patch in the data because we couldn't procure some spares for it. But you can see that the trends, the seasonal trends are similar, and the data is very comparable. And when we look at the Q10 value, it's also relatively similar. So what does this tell us? So the first question was, does fire exclusion lead to more soil organic carbon storage? The answer is no. It actually reduces topsoil organic stocks. It releases more CO2 to the atmosphere, and it has more temperature sensitivity, which means when you change a grassland into a forest, you are changing soil organic matter input from fine roots system into a litter system. And that affects the microbial communities also. So Afromontane grasslands show better sequestration than afforested sites or systems. So afforestation is not actually an effective climate change mitigation strategy for Afromontane grasslands, but maybe most for all grasslands. The second one is looking at aspect. We saw that south-facing slope is a better, it stores more carbon than the north-facing slope. So maybe it should be prioritized to be conserved in a grassy state. The last one is on soil respiration, and the two methods are comparable. The choice depends on the resources you have, how much money you have, and the specific research needs. Thank you. I'd like to thank everyone.
Thank you very much. We have time for a couple of quick questions. There's a question there.
Nice talk, Linda. Appreciate it. Just a clarification, I don't know if I misunderstood you. The two different sites, one you said was south-facing and not burnt, and the other one was north-facing and burned. Is that correct?
Yes and no. The one that we tried to exclude fire still come through. So there's a section that is not burnt, there is afforested, and there is a huge section that is still a grassland. It's maintaining itself.
But generally speaking, are you not confounding aspect with fire in comparing the two sites?
The two sites are comparable in the fire return. So they generally burn every second year because there's this buildup. So the accidental fire actually come from when they are burning fire breaks and fire escapes. So every time when they're burning other catchments and fire escapes into this catchment also. So we did look at that, and the good thing is there is Brotherton also. So the Brotherton does look at the differences in soil carbon stocks between annual burn and biannual burn. So we've seen how those differences affect carbon.
Really glad to hear grasslands outcompete woodlands.
I believe that. Thank you very much. We now have 3 short presentations, which I'm pretty certain are all associated with posters. The first is Session Dorsami, who will be speaking about long-term vegetation monitoring.
Right. Morning, everyone. I'm Sachin, and I'm going to be talking about long-term monitoring at FT on sites using CSO protocols. So we understand that there's a general increase in vegetation across Africa, attributed to plantations, alien invasive plants, and particular bush encroachment. And there's numerous factors for bush encroachment, which could be rainfall, an increase in temperature, change in land use, and an elevated CO2. Within South Africa, it's prevalent in our 2 largest biomes, grasslands and savannas. And it's predicted that with global change, that carbon stocks are going to increase in African woodlands. And we need to be able to quantify this change. The image on your right-hand side shows a 56-year change in woody cover in a savanna biome in Weenen in KwaZulu-Natal. So FTON aims to quantify this change using long-term monitoring protocols in an instrumented landscape. So I'm going to talk about CSO. So CSO is a social ecological observatory for studying African woodlands. It has an aim to understand the change happening within African woodlands. It is a network of scientists and a network of vegetation plots across Southern and Eastern Africa with an interest of understanding global change happening in African woodlands, savannas, and dry forests. The key outputs of CSO are standardized methodologies, ecosystem function and long-term monitoring plots. And these plots come from well-established protocols that have been tried and tested, linked protocols, and that can be comparable among sites, and more importantly, can be turned into long-term monitoring tools. So we see on the top left-hand side corner are the 6 FTON landscapes representing the different biomes across the country. The larger image is the CSO observation network. The yellow or orange circle means permanent plots. There are 5 permanent plots within South Africa, and the first one for FTON is at the Benfontein site, which Guy mentioned. So for the woody vegetation protocol, there are three objectives: to quantify change, to understand the relationship between growth, mortality, and productivity, and use these relationships and relate them to climate change. For the sampling, it's based on three things: plot size, with a 1 hectare plot preferred for long-term monitoring, and then tree stems are measured at DBH and at a specific diameter threshold depending on your site, and each tree is tagged. For the herbaceous protocol, it draws heavily from the global grassy group known as GGG, which aims to characterize richness and frequency. It's set upon 21 plots along a north to south and east to west system, and it's aimed that it could be turned into a permanent design for remeasurement. So within FTON's plan for design, everything is centered around an eddy covariance tower, which is a key instrument to measure the relationship between carbon and H2O. And since the measurement is greater than 1 hectare, we have modified the sampling design to be a central 1 hectare plot around the eddy covariance tower and an additional 4 1 hectare plots in each corner direction to make use of the measurable capability of the instrument. So within those 5 1 hectare plots, all the woody vegetation is measured, and within each 1 hectare plot, 21 permanent herbation plots are set up. So within KZN, we have 2 monitoring sites in the northern Drakensberg at Speenkop and at the MCP coastal plain at Lake Sabaya Grasslands. For the Speenkop site, it's a savanna with significant woody encroachment. It's protected, it's an Isabella reserve, has a history of disturbance. There's several large herbivore species. It has an inconsistent fire regime and surrounded by commercial agriculture. At the Lake Sabaya Grasslands, it's communal rangeland under tribal authority with a decreasing water table, significant livestock grazing, a variable fire regime, and significant resource harvesting. So for the Speenkop outcomes, the area is dominated by acacia, which I still love to call, and we sampled just over 1,000 trees and tagged just under 1,100 stems. The area is dominated by 3 acacias, Karoo, which is a known encroacher, Sibriana and Nilotica, and we aim to resample in the next 3 to 5 years. So for the Speenkop site, it's still ongoing for the herbaceous work. We have just only completed 1 central hectare plot where we just had about 150 herbaceous plants in the layer, and we aim to complete this in this coming season. For our Lake Sabaya Grassland site, it was dominated by 4 main trees: a known encroacher, Dicrostactus, Sidrax, Strychnos, and the Lala palm the Lala palm. Sorry. So the site has 342 measurable trees because given the nature of the site, it was a site where there were no tags. We sampled within a grid of 10 by 20 and each tree was geolocated. The cool outcome from this protocol was that we also did a small tree stem count and we count just over 2,000 Dicrostacus seedlings or plants. And we aim to start the herbaceous permanent plots in next year, January 2025. So I thank everyone that was involved in this protocol and helped me so much with this work. Yeah, thank you very much.
And you've finished with 2 seconds to spare. We'll field any questions later. Our next speaker is talking about the effect of rainfall reduction and resting periods on residual soil water, is Thabo Magandana.
Good morning, everyone. Like has been said, my name is Thabo Magandana. I'll be talking to you on the impact of soil reduction on rangeland productivity, soil water content, and selected soil chemical properties. So this is the outline of my presentation, where I'll be taking you through the introduction, objectives, materials and methods, results, and conclusion. The background of the study: this study was triggered by the impact of climate change that we are facing in our rangelands as we speak. So climate change is expected to result in water deficit, that is in soil reduction or water reduction in our rangelands. And this may affect soil properties such as chemical composition and soil water content. So understanding how the future drought might influence the soil quality and chemical properties is very important. So the objective of the study was to determine the effect of reduced precipitation on soil quality. The study was conducted at the University of Pretoria Heritage Experimental Farm at those coordinates that are flighted on the screen, and the annual rainfall is 674 millimeters per annum. The soil is categorized as sandy loam with 20 to 35% clay content, and the area has not been grazed since 1960. So there are no animals that are grazing on those sites. And the dominant grass species were Themida triandra, Aragrostis cavula, Aragrostis lemoniana, Ceteria nigrorostris, Tilteria riantha, and Heteropod condotus. So the materials and methods we used for rainfall interception strategies to exclude rainfall or to reduce rainfall on those plots, and they were 7 by 7 meters, that is 49 square meters in size, with a 25 centimeter a ditch which was excavated around the plots, where we made sure that there was no rainfall that comes underneath. We controlled the water runoff by that ditch which was excavated along or outside the plots, and the bands were constructed with a longitudinal plate of 120 degrees angle. Those are the plots where we had 0% rainfall interception, that is the control, where we did not intercept rainfall, and there's 15% rainfall interception, there's 30% rainfall interception, and 60% rainfall interception. The soil samples were collected from each subplot, which is the resting period of 70 days resting period and the 90 days resting period. And the two subsamples per plot were bulked together to form a homogeneous soil sample. The soil samples were oven dried at 40 degrees Celsius for 48 hours before sieving through a 2mm sieve to remove stones and roots. And the neutron water meter was used to measure soil water content. And the soils were analyzed for soil water content and soil chemical property. And those are the results. Rainfall result, reduction of 0% and 60% rainfall reduction did not show much difference in terms of soil water content, although in autumn there was higher soil water content than in summer, which I don't know what as to why the autumn would have high soil water content, but to think that it's because in summer there was high rainfall intensity, which might have resulted in water runoff, which did not penetrate on the soil. And the soil water depths had a huge difference, where the soil surface, that is the 0 to 20% to 20 centimeters depth had low soil water content as compared to deeper layers of the soil, which I think it is what was expected. And on soil chemical properties, the top soil, the top layer had higher soil water, had higher nutrient content than the 60%, than the 0% rainfall reduction, where the rainfall was intercepted at higher levels. We had high nutrient content, which is most likely the reason why we might have higher soil water content at 60% rainfall reduction. It was because of the low leaching that occurs at higher rainfall reduction. As we are saying on the conclusion, that this reduced rainfall could negatively affect the residual soil water content, thus affecting regrowth potential after defoliation by grazing or cutting and of the natural grasslands. The negative effect of the rainfall reduction in residual soil water content was more pronounced during summer than the autumn. In contrast, rainfall reduction was associated with higher extractable residual soil cations, partly due to reduction in leaching and partly due to reduced uptake by the soil of its nutrients by the plants. The rainfall reduction, however, did not significantly affect the soil pH, total nitrogen, and carbon, indicating the minimal impact of climate change, which is manifested in terms of the rainfall reduction and these parameters. I think, so yeah, that's the end. Thanks.
We'll have questions later.
Okay, we'll have questions at first.
Thank you. Sipolelo Takata is the next speaker who's going to be talking about growth and adaptive characteristics of tree seedlings.
Warm greetings to everyone and a good morning. As Mr. Takata Spell is my name. My study is on characterization of drought tolerance on tree lucent seedlings. This study came about from the changes that are occurring on climate, which has led to drastic weather extremes like erratic rainfall, increased heat wave, and also the drought. So singling out drought as the driver of changes of patterns on rangelands and also the biodiversity. So as the driver of changes in the biodiversity. So this has led to feed shortages, which is more drastic to communal livestock production. And there are measures that are undertaken to encounter these changes, but they are expensive and some are unaffordable. So this study aims at characterizing the ability of tree lucent seedlings to survive periods of water limitation and potentially identify the morphologically and physiologically mechanisms to survive. So the main objective of the study is to assess the growth and performance and the root architecture and the osmo or regulations. So we hypothesize that the roots, immediately the roots, or we hypothesize that the roots will explore high volume of soil to secure the edaphic factors, in particular water, and also the osmo regulations will be distributed. The concentration of osmo regulations will be distributed across different plant tissues differently. This table is an illustration of how the treatment will be applied, and it will take 35 days, and then with 4 water limited periods, that is 7, 14, 21, and 28, and 3 water regimes. So the application of this treatment will be systematically applied in such that all treatment combinations are harvested at the same time, and data is collected at the same time. And the specific outcomes of this study is to identify Trilocin seedling survival strategies and the resilience to different plant tissues to drought. And also this will lay a foundation in upscaling the production of Trilocin, also improving its adaptability, and also can be adopted in vegetation restoration, especially in South Africa as the low water limited country, which is rated as the 40th, and also which receives about 550 millimeters per annum. Thank you.
Thank you. If anyone would like to ask a question, we have a minute. Otherwise, if you haven't got a question immediately, we're now going to move on to a question and answer, not really question and answer, just a discussion time. So we've had all of these presentations, and I'd like to now open it up to the floor to ask any of the specific speakers a question, or if you want to ask general speakers and any of the general questions, and any of the speakers can answer. So I open up the floor. Perhaps I can just there we have it. Perhaps I can just start with one question to maybe all the speakers, but Guy, I'd like your input. There's a sort of global public opinion that we must reduce livestock numbers because of methane, right? And this has been called for quite widely. Now in South Africa, so this is the World on Data sites, Hannah Ritchie and so on, who produce all this fantastic data. Agriculture produces like 10% of, well, the total contribution of methane by agriculture to total emissions in South Africa equivalents is well less than 10%. And agriculture essentially accommodates 75% of the fabric of the country. The other thing is, if you look at agriculture, its contribution total methane is less than 20%, and the two highest culprits are fugitive emissions from mining, and then also landfill emissions. So that's actually open to any of the speakers. But how do we deal with this global public sentiment that we should be reducing livestock numbers, where it seems as though others possibly are more at fault? Can we have a microphone? Who wants to go first? Urs? Okay. Sorry, at the back there, at the back. Thanks.
Thank you, Chair. I think if my question is directed to the I forgot the name. I think it's Dlamini, the first presenter amongst the two Dlaminis. I'm sorry to say that I forgot the name. Yeah, yes, sir. I think when I listened to your presentation, I got a bit interested, and I just want to check amongst the factors that you look at in terms of the fire effect to the what is it, the grass production and the like. Do you relate, is it possible to relate that in future with the biomass yield, possible biomass yield of the grass, as well as the nutritive value, and connect to what the speaker says when it comes to the methane emission part, because that is one of the things that we are asked to do. Whatever that we do, we have to look at the possibility of reducing methane as much as possible. Why we are improving the production in terms of the animal derived food.
Yes. Thank you for that question. And I think to answer you, I would say yes, and because of two reasons. So NRF say on the biodiversity group, what they do more frequently is they collect grass species composition in the same plots, and then they also do DPM measurements for biomass yield. So yes, that can be correlated. Yeah.
Yes.
Yeah, great. I'm going to somewhat address your comment, Justin, and then also more broadly the cynicism that was brought up earlier on in terms of global afforestation, but also in terms of greenhouse gas emissions by agricultural production. I'm proud to say we've just had a manuscript accepted in PNAS where we compared carbon emissions across the North America from livestock production. And one of the things that became really clear is that it depends on how you measure it. So often it's just total amount of emissions per unit of production. But what we also looked at is per unit of economic value of the product. And that changed the equation entirely. So that was one of the results that came out. And I think that's one thing we really need to address when we're thinking about agricultural products. What is the value of those products? And look at carbon, greenhouse gas emissions, methane or carbon dioxide from a value perspective, not just from a production perspective. The other thing that also was part of the conclusion is that most of these studies do not incorporate the impact on the production system or the product. So we were comparing feedlots, for example, versus grass-fed beef, and they don't compare what is the additional greenhouse gas emissions that result from the production of corn for feedlots or from different grazing practices in terms of livestock production. So I think there's so many biases involved in these kinds of comparisons. And let's just be clear that the whole beef production incentive is driven by economic interests by individuals who have vested interests in trying to get diets changed from meat consumption to plant-based consumption. And it's failing, fortunately, in the United States. People are just not buying it. So that's one of the good things that is happening. But going to afforestation, it's the same kind of thing. I've got a great grad student working at the moment on this orchestration of native forests, which were never native, they were anthropogenic. And that's all driven by Eurocentric bias, where all of the sort of forestry management came from, where forests were not often burnt, where there were the climax plant community, and it's being superimposed on the rest of the world. And I think, especially in developing countries, people need to stand up and say, this is a sort of a new imperialistic effort to try and impose values on people where it just doesn't fit. So I think there's a huge amount of work to be done in that area. So I work with Joe Feldman, who you probably know of, Guy, and he first came out and criticized this whole afforestation drive that came out of Switzerland, of all places, I'm embarrassed to say. So we need to address it and address it squarely and really point out that these kind of initiatives have really, really serious long-term ramifications that will not be easily reversed.
Thanks, Urs. Yeah, they're back. Where's the... Yeah, go for it.
Right. Can you hear me? How many of you know about the UNCCD convention, United Nations Convention on Land Degradation and Neutrality? Hands up. Okay. I want to introduce the concept of talking in an echo chamber. If we keep talking to each other and we don't start influencing these policies, we're not going to have an impact. And at the moment, the DFFE are busy reviewing South Africa's National Action Plan on Land Degradation Neutrality. And they are seeking nominations for people to look at these sorts of things. But I'm just wondering if the Grassland Society doesn't have a vital role to play to actually coordinate a policy piece that actually goes to them so that they can be informed by science. One of the outcomes is outcome 3, which is encouraging research around this and how to achieve it. And I just want to plant the idea that we need to synthesize this and start shouting more loudly at our own negotiators so that appropriate decisions are made. And there is a current initiative to actually do that. So if anyone's interested, please come and speak to me and we can try and influence our own politicians first.
Thanks, Sue. Guy?
Yeah, well, I think the afforestation idea was first suggested by the physicist Freeman Dyson in the 1970s. And I mean, he did great work in quantum electrodynamics, but he didn't understand ecosystems. I mean, I think a society like this does need to understand the risks. There is a kind of a global war on meat. There's a global obsession with vegetarian and veganism. These studies in the north that are saying, you've got to switch to more healthy diets. So, but the two issues are ecological health and human health. And we know that human health, you run into problems if you move too far away from a meat diet. And I think we need to fight our corner, because what else are you going to produce in the Karoo? We have natural rangeness, and this international pressure, it has the inadvertence. I'm sure it's not intended, but it has a real impact on our cultures and our livelihoods. And it's the same with the afforestation story. There's big money behind these things, huge money, and it is tied in with vested interests. But we need to understand it, and we need to warn our politicians and our negotiators not to get trapped and caught in these agendas, because they will backfire badly. So, yeah, let's stay awake.
No? Yes? Okay. Yeah, just you mentioned Freeman Dyson's paper from the 1970s. I actually recently read it, and it's a hoot. But it just shows you how, and I will tell you now why, how something that someone famous put out there, outlandish as it was in the 70s, gets snapped up by vested interest. So Freeman Dyson, his paper is, the idea was that should, in the highly unlikely event, carbon dioxide should reach levels that are somehow dangerous to us, would it theoretically be possible to plant enough trees to take it up? And he says very clearly, this would be a short-term stopgap. It would not be a permanent solution, but it could be done with an insane quantity of fertilizer. The cost would be astronomical. It would be a bit more feasible if you could do it in countries where labor was cheap. And he said the other possible organism of interest that could maybe be considered is water hyacinth. So, I mean, if you read this paper now in the 2020s, you just want to roll around laughing. But it is a physicist's paper that states very clearly, all I'm saying is, could it happen? It would be completely ridiculous, but you could in a case of emergency, do it as a stopgap measure. But this sort of thing gets picked up on and becomes gospel, and you completely forget what the original actual paper was about. And yeah, and I think a lot of it is vested interest, and we really do need to resist it.
Here we have a question, and then Linda.
Hello, everyone. I have a question, and I don't know if it has been answered before or asked. What mitigation strategies, apart from agroforestry, can effectively improve indigenous biodiversity in grasslands affected by mineral extractions and soil erosions?
You would like to address that? Do we have any takers for that question? It was too complex a question. Maybe while people are okay, let's have Guy, and then we'll go to Linda.
Well, I think it's a great question, because perhaps there's a market for restoring these systems and recovering carbon in them, and it's another argument for monetizing or funding that kind of restoration. I think there are many elements to how the land has been degraded that would affect the strategy that's followed. But there is a very active ecosystem restoration community in the country working on these topics in many systems. And they are looking at the carbon value of their work as a way of earning additional finances to do this kind of work. So I think those kinds of interactions would be useful. I don't know particularly specifically of a community looking at the examples that you mentioned, but if they're not, there should be. So, and if you have agency to get that going, then I would strongly encourage you to do so.
Thanks, Guy. Linda, you have a couple of questions from the
Okay, yes,
virtual delegates.
online there's been some discussions about the Drakensberg and altitude and aspect with Debbie and Jewett, and she has commented that in the Drakensberg it's more complicated due to geology confounded with altitude. That was to do with Linda Dlamini's talk, I think. Topography would play a significant role in soil depth. There was a discussion going on about soil depth in the Drakensberg. And a comment by Antoinette Aisel: well-managed livestock farming on natural grassland play a role in conserving those grasslands, and the carbon it stores, and is far better than ploughing up land for alternative proteins such as nuts and soya. And then a comment from Sigrun to say, I agree with Urs that the parameters included in the measurements or are not included affect the outcome. Very often a narrow set of parameters is preferred in the calculations. For instance, for dairy production, the calculations of concentrate feed production, for example, emissions of maize production or the manufacture of fertilizer, etc., might not be included. So there's some comments from online. I don't know if anyone wants to field it.
Devin had a
make a comment to address this question here about following up on mineral extraction in the north. I think it comes down to a policy thing, but there's also some logistical constraints in South Africa. But in North America, anyway, especially in Canada, where they're a little more environmentally conscious, before any mineral extraction occurs, there has to be a full environmental inventory, and they're looking at what the diversity and the productivity of that site was before they initiate the action. And then whether it's something small like a well pad or whether it's as large as like an open cast mine, a lot of times they'll strip off the topsoil first and store it, put it in a pile, and then subsoil is handled separately. And then it's put down in that reverse order. So subsoil is put down, and then the topsoil is put down, and then it's revegetated. And especially in the case of like an open cast mine, but also the well pads and pipelines, the company is actually under bond to restore that to its prior productivity before they can be released from liability for that site and say they're done with it. And so that just comes down to the laws and regulations requiring that assessment to be done, so they know what that baseline is and what it needs to be gotten to, and then having the knowledge to do it. And in South Africa, I think a question would be whether you have the like native seed market, commercially available native seed, and then the knowledge to drill that, well, literally to drill that in. But I think it comes down to that keeping the topsoil separate and not getting it all aggregated is really important in terms of being able to get something to grow there afterwards.
Thank you. I'm going to end it there. What a great session. Thank you all for interacting so much. I think that it's this is such an important issue. We need to move forward as a society on it. We need to interact with others and partner up with other people. But to all of the speakers, thank you so much, Guy. Thank you so much for coming through. Everyone, a round of applause. Thank you.